En la casa nos pueden ver todo, ¿ok? Parece que no nos escuchan en la casa.
Sí, todo bien.
Perfecto. Let me see if I can move this out of your view here. 1 second. Here. Now, we have move here. And let me show the test if the clicker is working. Yeah, thank you. Wonderful. Muchas gracias. Bienvenidos a todos al seminario del doctorado en Ingeniería y Ciencias con la Industria. Hoy día tenemos este es nuestro primer seminario, así que lo inauguramos esta sección. Adelante, ahí hay harto espacio, así que avante, avante. Y vamos a iniciar nuestras series, esperamos mantenerlo, así que bienvenidos a todos acá, presenciales y en las casas. Y hoy día tenemos el honor y el placer de contar con Justin Payan. Y en honor a él voy a transformarme al inglés porque nuestra charla va a ser en inglés. Justin Payan is a Postdoctoral Research Associate at Carnegie Mellon University, developing AI, optimization, and social scientific methods to improve scientific productivity. Can that be done?
We're going to try.
Excellent. He received his PhD in computer science at the University of Massachusetts Amherst, and he's currently working with Professor Rodrigo Carrasco, and he's going to present his work, Optimizing Scientific Productivity. Hey, I can do that a lot. Thank you.
Great. Thank you so much. Yeah, thank you everyone for hosting me at the seminar today. So I'll be talking about optimizing scientific productivity. In science, we are often concerned with how to allocate scarce scientific resources. Practical examples of this, so for example, peer review is one method of allocating scarce scientific resources. There's scarcity in space for published manuscripts, and scarcity of attention for what manuscripts are worth paying attention to. Another example is instrument usage. So in many fields, there are expensive instruments. We have to figure out how to allocate those instruments. Who gets to use time on those instruments? We have to regulate how are these instruments made available. Funding is another major example. So this is kind of the universal resource, right? How do we allocate money to scientists to do their research? And finally, time and expertise, right? So how do we, many of us have deep expertise in some topic. Our time is very valuable. How do we allocate that time? How do we make sure it's used efficiently? So we often have some sort of solution for allocating these resources, but we may not have a clear answer of this is the best way to allocate this resource, right? And being able to improve these systems might mean more major scientific discoveries. It might mean saving huge amounts of money in some cases. And again, it may mean using experts' time, very limited time, more efficiently. So the goal for each of the projects I'm going to talk about in this talk is to identify scientific systems and workflows that could be improved. We'll talk about how to define metrics for success in these systems, and then how do we optimize some of these metrics. And by the way, if anything is unclear, definitely stop me at any time. And I'm happy to go into more details on things or clarify any clarifying questions. So I'm going to talk about 3 major projects that are focused on optimizing scientific productivity. The first, and this is the reason that I'm here in Santiago, is working on the telescope scheduling problem. That's the work that we're collaborating with Rodrigo on. Then I'll talk about automated reviewer assignment for peer review. And finally, I'll talk about some recent work looking at how we can use AI for error detection to support peer review. At the end, I have a couple of slides talking about some kind of future work looking at using AI and optimization towards scientific productivity ends. So let's start with the telescope scheduling work. Noemi is here today, undergraduate working with us at Carnegie Mellon, and Rodrigo as well is working on this project. And this is in partnership with a couple of people at the ALMA Observatory across town here in Santiago. So the ALMA Observatory, or the Atacama Large Millimeter Submillimeter Array, is an array of about 60 antennas located in the far north of Chile in the Atacama Desert. They do a lot of really interesting astronomy and important astronomy work. I just picked a few examples, but they've contributed a lot to our understanding of planet and galaxy formation. And as a computer scientist, I had heard of the imaging of the black hole at the center of our galaxy, Sagittarius A star. ALMA was part of the partnership that produced that image in 2022. So that was kind of an exciting thing for me. So ALMA does a lot of important science, but who actually gets to use ALMA? Last year, astronomers from around the world requested over 7 times the amount of available observation time on the telescope array. And ALMA is very expensive to operate, right? So that they estimate their yearly operating costs are like $100 million US dollars. And annual hours spent observing is about 4,000 hours. So this comes out to about 25,000 US dollars per hour. So if we can improve this even a little bit, get say a day or two of extra efficiency out of the telescope, that would be already quite something. And generally, their system for allocating time on the telescope works as follows. So they every year request and review proposals to use the telescope, and then they operate the telescope in what's called service mode. So this means instead of having astronomers actually come down and operate the telescope themselves, there are employees of ALMA that perform operations on the telescope in service of the other astronomers who have submitted proposals. So our task is going to be scheduling in service mode, helping with operations for scheduling observations at ALMA. Just to give you a sense of what the yearly cycle looks like, this is an example from a couple of years ago of their major milestones throughout the cycle. So sometime around March, they'll release a call for proposals. They then have an extensive review process of those proposals, during which they will rate the relative importance of observing each of the different proposals, and they'll also tweak what the requirements of each of the observations are. And then in October, they'll actually start the observing cycle. And this is sort of the moment where we come in. After they've kind of pre-processed all those proposals and ranked them and said these are the most important ones, we then come in and try to provide scheduling algorithms for actually operating the telescope through the year. So I want to give you a little bit more sense of how they rate the proposals. So after they've gone through the peer review process, they have a set of ranked projects, and each project consists of potentially multiple observations that need to be completed. These observations are typically an hour or two in length. And basically the top 100 or so projects will be categorized as A grade, and these are treated as high priority by the telescope. The next few hundred or so will be categorized as B grade. These are medium priority, so they're still aiming to complete most of these projects, but they're not as important as the A grade. And then anything else is grade C, that's filler. If there's some outside reason that they need to run these, we'll talk about what that might be in a minute. they may run them. Or if there's no A or B grade things available, they may run a filler. Now, a very important thing to note is that the availability of any observation depends on the time of day, the time of year, and on the conditions of both the weather and the antennas themselves. So there's both deterministic requirements that are just based on time, as well as stochastic requirements. So we don't know what the weather is going to be like, but it has to be at least a certain amount of observability for each observation. Another constraint, this is a global constraint, is called executive balance. So each of these projects comes from one of 4 different executives. These are agencies that participate in ALMA. So they were part of the founding of ALMA. They've contributed funding and continue to contribute funding to ALMA. And they're part of the governance of ALMA as well. These are North America, Europe, East Asia, and Chile. And ALMA is actually obligated to allocate time to these executives proportional to their participation in ALMA. So it's about 30% of time is earmarked for North America and Europe, about 20% for East Asia, and 10% for Chile. Okay, so those are kind of the major contours of the scheduling problem. Let's now look in more depth at how we actually go through the cycle. So in our modeling of the problem, we assume that we have a 30-minute time interval throughout the year. So there's about 17,000 30-minute intervals in 1 year. Given our set of ranked projects, observations, and all of their constraints, we can think about every 30 minutes, we view the system state. If there's an observation that is currently executing on the telescope, we can move to the next time step. If the telescope is free, we have to figure out what do we in queue on the telescope. And then finally, at the end, we'll have some set of completed observations and projects for the year, and we can evaluate how did we do. So the metrics that we're interested at the end of the year will be how many A, B, and C grade observations were completed, as well as same, we're interested in how many projects were completed of every grade. We're also interested in how much of the usable time was spent actually observing versus idle. And finally, did we meet the executive balance targets, or at least did we come very, very close? So these are the things that we're going to be targeting. Let's talk a little bit more about what this system state actually includes. So of course, it includes the project and observation completion up to that point in the cycle so far. It also includes what is the weather like. I briefly alluded earlier to the fact that you have to look at the state of the array itself. So ALMA can actually move the antennas around, and that provides different capabilities. So some observations will require a particular configuration of the antennas. These antennas are very complicated technical instruments. So it actually often happens that something is wrong with some component in some antenna. So we have to keep track very closely of the antenna availability, as well as particular instruments within each antenna. And finally, they have roughly weekly maintenance windows, and occasionally there's some software glitch that leads to technical downtime for the whole system as a whole. So all of these things are included in the system state, and we have to keep this in mind when we're scheduling things in real time, but also try to forecast these as we move through the year. So let's break apart how do we actually enqueue an observation on the array. We take our 4 metrics and formulate an objective based on them. So we provide a set of configurable weights, W1 through 4, and have a weighted observation completion component, a weighted project completion component. The utilization rate can directly be expressed in this objective. And then finally, we have a penalty for violation of the executive balance targets. This is expressed as a sum of squared differences from the target values. This last part is actually not something that had been included in their prior dynamic scheduling algorithm. So we've seen it's quite helpful for meeting executive balance, and we'll see that later in the results. Okay, so this is our objective essentially. But now let's look at the algorithms that we actually use to achieve this online. So we can think about unrolling the loop that I showed earlier, right, where we view the system state and then enqueue an observation every 30 minutes. We can think about unrolling this throughout the yearly cycle. And we think about basically three tiers of time frame. So the first is a greedy time frame. This is how the current dynamic scheduling algorithm that they're using at ALMA would work. It only considers what the current conditions are, and using that we can tell, okay, we can run this observation but not that observation, and so we'll pick A or B, right? The second time frame that we look at is a short-term look-ahead time frame. So we've set this to be 8 hours. And at this short-term horizon, the conditions are basically stable enough to plan at the 30-minute granularity. So we can consider a look ahead and say, what can we actually complete according to our objective over the next 8 hours? This would be usually like 4 or 5 observations worth. And then finally, we have the long-term look ahead, which considers our predictions for the rest of the cycle. And this is much more coarse-grained. So at this horizon, we're looking at assigning observations week by week rather than 30 minutes by 30 minutes. And we're still optimizing for the same objective, but just at a coarser time scale. And once we have a long-term solution, we can use that to assign bonus values to observations in the short term or even in the greedy immediate term. Any observations that were planned to be taking place this current week, we can give them a bonus. And we actually repeat this optimization every week, so we always have a fresh long-term schedule. I definitely should mention that this strategic long-term look-ahead problem was originally something that Rodrigo and one of his students, Camila, worked on. And Noemi worked on helping to integrate that with the rest of the schedule. So on this slide, I have the results of incorporating all of those improvements compared to the current scheduler that is used by ALMA. On the top, we're showing in yellow the current versus in red the proposed algorithm. And we have the delta from the executive balance targets. So anything lower than the target or higher than the target is not desirable. And we see that the current algorithm that they use at ALMA for automated scheduling, they also do manual intervention, but the current automated scheduling algorithm does not meet the executive balance targets, whereas with the inclusion of our executive balance penalty, the short-term look ahead and the long-term look ahead, we're able to pretty closely meet the executive balance targets. On the bottom, we have the other metrics that I discussed. So the two leftmost columns, we have the completion rate for A grade and B grade observations, then the completion rate for A and B grade projects, and finally the percentage of schedulable time that was actually utilized. So the utilized time is the same between the two, but we see an increase in A and B grade observations and projects from including all of those improvements. And like I mentioned before, this is only plus 30, plus 60 observations, but that amounts to a day or two of extra time worth on the telescope, which is actually quite a useful improvement. Noemi has also been hard at work on dashboarding tools for comparing different algorithms, as well as comparing the weight settings in our objective. And so while we're down here, she's been integrating that into the workflow of the ALMA data scientists and the scheduling tools. So that's very exciting as well. Cool. Thank you. Any questions about the telescope scheduling? Right?
Because when you have major movements of the antennas, that's not part of the scheduled time that you are accounting here. Because if you take into account when you're selecting the projects, the configuration of the antennas, you might be able to even increase the amount of time that you might be able to schedule. But that's not part of the project to increase the amount of time available.
Are you asking about determining how to move the antennas around?
Or the setup? Because every time you sort of schedule a project, you have a setup time in probably moving antennas and
yes,
reconfiguring them, and just in the way you might order projects might affect that available time.
Yeah, that's a good question. So I know Rodrigo and Camila, when they were working on the strategic scheduling, they actually looked at shrinking, growing or shrinking the available time in each configuration. I believe the configuration calendar is set ahead of time for a number of reasons. I think one is they need to have it roughly set in stone so that when the astronomers submit their projects, they know, like, okay, we're going to be in configuration 3 in March. So I can observe this thing, right? So you have a little bit of flexibility, but we can't basically pick out of thin air, you should do this then, right? So, yeah. Any other questions? Cool, thank you. That was an interesting question. So for this part, I'll be talking about our automated reviewer assignment algorithms. And this was joint work with Yair Zik at University of Massachusetts Amherst. So in many settings, we have to assign many reviewers for peer review all at once. This actually shows up in telescope proposal review because they get their proposals submitted in March, and then you have a few months before we start observing. So they have to assign a bunch of reviewers to a bunch of proposals all at once. But there are many other settings where this shows up. So for example, certain types of grants might be submitted and reviewed in a block. And I don't know how it is in industrial engineering, but in computer science, we have conference proceedings that are reviewed nearly as rigorously as a peer-reviewed journal venue. And so this causes a big block of reviews to be needed all at once. But we can't just assign random people to random papers. Scientific review requires people that are subject matter experts on the topics they're reviewing. But these batches are often really large. So ALMA, for example, last year received over 1,600 proposals. And NeurIPS is one of the major machine learning and computer science conferences. Last year, they had over 21,000 submissions. So obviously, this is not something that a central committee could review, and it's not even something a central committee can field reviewers assigning to. Okay, so this necessitates algorithms that we can use to assign reviewers to submitted manuscripts or proposals. We need our algorithms to be somewhat fast, somewhat scalable, because we have a short time frame in which we need to complete our reviews. We want to assign the right reviewers overall. So in general, we want subject matter experts to be assigned to the right papers. And we want to ensure any individual paper or small set of papers receives adequately matched reviewers, right? You might imagine maybe overall we have a good assignment, but some subfield gets totally inappropriate reviewers, and we wouldn't want that to happen. So this is sort of a fairness constraint imposed on the boxes. So in this work, we developed an algorithm called fair sequence. I'm just going to very briefly go over in general how it works. The idea is that we first take the set of papers that the reviewers have published in the past. This is sort of a representation of the reviewer's expertise. And then we can calculate the reviewer's fit with any submitted papers or submitted projects using something like topic models or a deep learning model, or often these venues will solicit bids directly from the reviewers. Just ask them, which of these papers do you think you could review? This part is fairly standardized at this point in the reviewer assignment literature. So our algorithm is not really focused on this part. We're just assuming these are given. What we're more interested in is how do we actually allocate the reviewers once we've estimated their fit to the things they have to review. So the basic idea of the fair sequence algorithm is it's a picking sequence algorithm. This means we put the papers into some order and assign reviewers in that order greedily. So when it's some papers' turn to be assigned a reviewer, we just pick out what's the best fit reviewer that is still available. That's the next reviewer that we put on that paper. But the key thing is we choose this order carefully so that we end up with a high overall sum of the fit scores, and so that we end up with a fair allocation of the reviewers. So I'll give just a little intuition of how we might do that. You could imagine, for example, choosing this as our order, right? Maybe if we need 3 reviewers per paper, we might assign all 3 to the orange paper, and then assign all 3 to the green paper, and so on and so forth. But I think you can easily see that by the end of this sequence, we're going to end up with papers that have basically no suitable reviewers left. So if instead we do something like this, where every paper gets 1 high fit reviewer before we move on to the second reviewer for every paper, this is much more fair. And this is really the basic intuition of the fair sequence algorithm. We can show that if we choose a picking sequence that is more similar to the bottom one, we end up satisfying a fairness notion called NB freeness up to 1 item, or EF1. And we also show in our paper that this fair sequence algorithm has some approximation guarantees on the sum of the overall fit scores. It's also very fast. So this algorithm is quite simple. We just put papers in some order and assign the top reviewer one by one. So we've compared against 3 other reviewer assignment algorithms. And on some of the data sets we run, the fair sequence algorithm is 1 or multiple orders of magnitude faster. We also compare the sum of the fit scores and the number of violations of our NB freeness up to 1 item fairness principle. Of course, our fair sequence algorithm is designed not to violate the fairness principle, so we have 0 violations. But interestingly, we see some of the other algorithms can have a very large number of violations of this fairness constraint. We do see a slight decrease in the overall sum of the fit scores in fair sequence compared to some of the other reviewer assignment algorithms we compared to. But that is a trade-off that the conference organizers or the grant review organizers can decide on. So we've implemented our fair sequence algorithm in the openreview.net peer review platform. This is a major platform that a lot of the computer science conferences use to host their peer review. In that platform, you can pick which assignment algorithm do you want to use, and over 50 peer review venues have used this algorithm as of several years ago was when I inquired about how many people have actually used it. Okay. Any questions or okay, so the last thing I'm going to talk about is using AI for error detection. So this is less about assigning resources and more about using peer-reviewed resources more effectively. This is joint work with Serena, Vishisht, and Nihar at Carnegie Mellon. And this was done this last year. So many people are starting to use AI to actually perform parts of peer review or to aid in performing peer review. For example, the AAAI Computer Science Conference this last year piloted a tool that uses AI to produce a separate peer review that is shown to the authors and the other reviewers during the review process. There was also one other conference, the International Conference on Learning Representations, another major peer-reviewed computer science conference that did a similar thing this last year. And overall, these pilot experiments are receiving generally positive feedback. Anecdotally, people have noticed that sometimes these automated peer reviews can identify problems in manuscripts that the other reviewers didn't identify. But there's kind of a lot of debate about how to actually rigorously evaluate these things. How do we actually trust the LLM to spit out a peer-reviewed paper, right? So some of the things that have been suggested include comparing against past reviews, or perhaps just having a holistic kind of review of the review, right? But there are a couple problems with both of these. So when we think about comparing against other human reviews, one issue is that, well, there are some publicly available reviews, but if they're publicly available, there's possibly some training data leakage into the AI models. In addition, so my postdoc supervisor, Nihar, has done a lot of research on various ways in which peer review can fail. So for example, there have been several studies where they deliberately insert errors into papers and then try to see if they get caught by peer review. And on average, these kinds of errors get caught like 30% of the time. And there's numerous other biases that may occur in peer review, including all the way up to fraud. Nihar also has a line of work looking at collusion rings in peer review. So I had not known about this before, but apparently there are people that will say to each other, hey, I'm going to be a reviewer. You sign up to be a reviewer and we'll accept each other's papers. So yeah, there's a lot of weird stuff that happens with human peer review. We can't always treat it as a gold standard. Yes, yeah. Apparently they've uncovered like major rings of these things. So it's not just reciprocal. It can be like 20, 30 people that are sort of doing it in a convoluted way.
That's a mafia.
What
Yes.
are you coordinating?
Yeah, I know. It's very impressive.
The need precedes the award.
Yeah. There's an algorithm to do the coordination. I don't want to do it.
That'll be my next work. That's future work.
If you put that much effort in coordinating, you should have put it on the paper.
Yeah.
There's a paper there, right?
Okay, so the other thing that we might do is holistically evaluate these peer reviews, right? We can ask other experts to look at these reviews and say, what do you think? Well, a big question is, who do we actually ask to do this, right? The authors of a paper are probably the most suitable for this because they know the subject matter the best. But for obvious reasons, they're biased towards positive reviews. They're going to say, oh, the LLM liked my paper, great review. Oh, the LLM didn't like my paper, terrible review, right? So it's hard to disentangle the suggestion of the review from the quality of the review. Now, if we ask other people, like say maybe the other reviewers of a paper, the human reviewers of a paper, this is other work that Nihar and some of our colleagues have worked on. There are other biases that people exhibit when reviewing peer reviews. So a couple of years, or actually last year, they did a randomized controlled trial where they inserted meaningless text into reviews. And they found that if you ask somebody which review is better, they'll pick the longer one, even if it's longer for meaningless reasons, right? So for all of these reasons, these are not necessarily perfect options. So we go back and think a little bit more about what are the objectives of peer review in the first place. One of the major objectives of peer review is to detect errors in manuscripts. In many ways, this is kind of more objective than general subjective human judgments, right? If you know that there's an error in a paper, you can, there's some fuzziness, but you can more or less tell, hey, did the AI pick up on this error or did it not, right? But this brings up a few more problems, right? If we want to evaluate by can AI detect errors, well, mainly, where do we actually get papers with known errors in them? So one option is to use articles that have been retracted, but this is a very small proportion of the overall literature. These would be very high quality gold standard errors, but it's a small amount. And again, it has the issue of training data leakage. Another option, and this is something that people have done, is to look at papers that have been withdrawn from archive. So when you withdraw a paper from archive, you can leave a message saying, here's why I withdrew it. And sometimes these messages say there was a flaw in theorem 7 or something. The problem with this is that there's really no quality control, right? So if we want to evaluate the ability of AI to pick up on errors in papers submitted to a high quality journal or a high quality conference, this may not be the right distribution compared to that. We also have similar problems to using existing review text. Again, training data leakage, there may be certain biases, and so on. So our suggestion in this benchmark, and what we do in this benchmark, is deliberately insert controlled errors automatically into manuscripts and then try to identify them. We take a paper, take the LaTeX source of a paper, identify a major claim of the paper, and then we ask, again, an AI, please modify text in this paper so that this claim is no longer validated by the information in the paper. So we then end up with a modified paper that is broken, and we know exactly where it's broken. We can then ask the AI, do you find any papers in this, any errors in this paper? And if so, please reproduce the text that is erroneous.
Sorry,
Yeah.
do you have there a circular reference error? Because you're asking an AI to produce the error and an AI to identify the error.
Yes.
Why don't you make a person or a researcher make the error and ask the AI to detect the error?
Yeah, that would be ideal. The problem is that that's not scalable.
But the same problem you have with retracted papers. They're small, but I think that it might be because then you have a circular reference there. So it's just you're proving that he is able to see himself.
That may be true. So one thing that we do is, generally in our paper, we're suggesting kind of a general method for doing this, but when we actually construct the benchmark, we use multiple models. And so you can evaluate, okay, ChatGPT inserted errors. Now Gemini is identifying the errors. So there's at least that kind of cross-checking. We also did some manual annotation of the errors. So it's not perfect because not everything will be
but still
verified.
You're probably identifying an AI probably, and the AI is identified. This was made by an AI. Okay, so how do you actually take that outside? Because one of the things they put your paper through is detecting if it was produced by an AI or has a large percentage of what you do made by an AI.
Yeah,
and what you're probably detecting is that it was made by an AI, but you're not detecting it's really an error.
That's an interesting point. That could be a possible confounder.
Just bringing some ideas.
So I guess one thing is that these are typically fairly short snippets of text, so that may help with that. I guess the other thing is if we're seeing very high performance, then I would be concerned that it's because of that. you can decide if you think the performance is high. I think it's the next slide. So the top accuracy that we got was 40% for identifying errors. So yeah, you're right. It is possible that some of that is just identifying, oh, this looks AI generated. But I mean,
Yeah.
if the performance were 90%, I would be more concerned about that.
I didn't see that.
So, one other thing that I didn't actually put on the slide, we have multiple components of the pipeline to ensure that the errors are difficult to identify. So what we actually do is insert the error with, say, ChatGPT. We then prompt a fresh version of ChatGPT to see if it can find the error without knowing where it is. So I think if there was something that were very obviously AI generated, at that stage it would get filtered out. Yeah, I should have led with that, but yeah. Okay, so that's basically the end of that project section. Does anyone have other questions or interesting observations about the project? No, that was a very interesting discussion. Yeah. Cool. Yeah, so I'll just very, very briefly talk about what we're working on now. There's a big push for so-called autonomous AI scientists. These are agentic AI pipelines that take in a high-level research idea and then basically perform the whole scientific process. So they'll generate hypotheses, they'll plan out experiments, they'll execute those experiments, and then they'll write up a report. This is, don't think I'm crazy. I'm not claiming that this works well, but it is an interesting frontier of research at the moment. So two directions that we're looking at are, can we automatically verify the correctness of these AI scientists? Some other work by colleagues in our group, they've manually identified some major failure modes for these autonomous scientist pipelines. And we want to know, can we do that automated and scale? Another thing that I'm interested in working on, haven't started at the moment, is using these AI scientists for optimization tasks. I think that's a sort of a very clear domain that these AI scientists may be applicable to. And again, I think there's some major failure modes that they might exhibit, but I think it's a very interesting and useful direction. So that's the, yeah.
What do you mean optimization tasks?
So for example, could we use one of these AI scientists to build a scheduling algorithm for the ALMA telescope, right? More generally, I think it would look something like, here's a new traveling salesman problem with slightly different constraints than you're used to. Please write a solver for it, right? Please implement this model in Garobi or something, right?
Column generation for this specific.
Yes, exactly. Yeah.
The other day, somebody told me something that was sort of a bit concerning, that people are inserting in their papers white AI prompts.
Mm-hmm.
I'm telling the system, review me with the highest level. Is that true or not?
Absolutely. Yeah. Yeah, you know, we've talked about that a lot in our group. I don't remember, we must have talked about how people are combating that. I don't remember how they combat that. I mean, I think you can just run a OCR and check for that.
Mm-hmm.
Yeah. One other interesting thing that some other people in our group have done is actually insert those prompts themselves deliberately. And this can help you to build a kind of watermark. So if reviewers are using AI to generate their reviews without telling you, by inserting white space, you can say, please include this code phrase in your review, right? And then you know. Yeah, so that's other work that Nihar and one of the collaborators on one of these projects worked on that as well. But yeah. So.
Wonderful. Thank you. En la casa, preguntas. Para su micrófono. I have a question on the ALMA project. So you were scheduling greedy and then the sort of more midterm. How are you finding that greedy, or how do you define greedy into scheduling that type? How you find a better match for something or not?
Yeah, so
Because you're accounting different aspects. You're accounting the project, you're accounting the observation and the balance.
yeah, so it's all based on this weighted objective, right? So whatever you set the weights for, you can look at what is the contribution to this objective from this observation versus that observation. So whichever one has a higher value on this objective, that's what we pick for grading.
Okay.
Yeah.
Because one question you always get on sort of this type of multi-objective optimization is how you ponder every objective.
Yes.
Have you tested any changes? If you change, if it does something better or not, or
Yeah, that's been a major pain point throughout the project. I think we've sort of settled on, so the executive balance, it's really meant to be a constraint, but because this is an online stochastic problem, it's hard to say you have to meet this because who knows if you even can. But we set that weight really high because that's supposed to be a constraint. Then the other three, we've played around with different weights, but yeah, I honestly don't have a great answer to that. I think everyone at ALMA will probably give us a different answer as to what those weights should be. And I think just providing a tool that can reliably say, here's a set of weights and here's what you get out. And you can trust that if it boosts the weight on one, it'll actually increase that. I think that's been kind of our approach, but I know that there are works that look more at like optimizing the Pareto front, for example, and we haven't done anything like that. So yeah.
And related to the studies, you have a project and an observation. Are the observations within a project too different between each other? Because are there sort of something that you say, hey, I need really to weight this, or I just look at the observations and I'm also optimizing the projects?
Yes. So this was something that I simplified for clarity in this presentation, but absolutely. So for example, you can have observations within a project that are observing different frequencies, and ALMA, I think in the last several years, has upgraded or has some special equipment to observe very high frequencies. So one thing that I keep hearing all the time is high frequency observations are a priority, right? And that may not be the whole project, that may just be part of it. So absolutely, they may have certain observations within a project that have priority. And our implementation can handle that. I just kind of push that under the rug for clarity. But yeah.
You could even have it throughout the year. Like you want to observe, 3 pulsars, and one is on the Senate, in March, the other one is in October. So you have to. This project has observations throughout the year, not just in one moment.
Okay.
Yeah. Well, and initially I thought you were asking, can they have different constraints as well? And absolutely, they may. Observations within a project may have wildly different constraints. Yes.
Is there in ALMA a protocol for unlikely situation that might happen? For instance, when a supernova explodes, the protocol of the entire world is every telescope in ground telescope must observe the supernova.
Yes.
Is there something included in here, or is it too exceptional to be included?
Yeah. So our feeling was, and working with the data scientist who works on scheduling tools at ALMA, our feeling was like, initially, let's not try to model those rare events, but absolutely, they obviously do have those rare events and they observe them. So the thinking was, if we can get kind of most of the time the benefit from this scheduling tool, and then suspend it when there's a supernova that you didn't expect. And of course, you'll point the telescope at it. Yeah.
Yeah, there's some time that's called like director's time. So
Yeah.
the director of the telescope just, point everything in that direction. Like what they did with the black hole, they had, it was sort of a multiple arm gambit sort of type of thing they were using, because they had to 2 or 3 times they could actually call from the Event Horizon telescope and say, you know what, we need to observe this. But they had like 2 or 3 calls throughout the year. And when they called, the director had to say, stop everything and put the telescope in that direction.
This is very important.
And that's part of it. But you can think of that as well as like, it's cloudy today.
Yeah, it's a perturbation.
It's just a perturbation of the weather or whatever, right? And it's the same thing for what they're doing.
Yeah. I mean, the only issue is that we don't really have a model, like for some of these events, we don't really have a good model of. And also, I'm not an astronomer, so I can't model when is there going to be a supernova, right?
They don't know either.
And here, because if you start an observation, you're also trying to forecast the future. Because if you start an observation and you see the humidity going up, okay, maybe that observation should not be set. Your model looks at that also when it.
Yeah, so this, I don't actually have a slide on this in this version of the talk. Tomorrow I'm giving a different version at ALMA that has this. So we made a simplifying assumption that based on the conditions now, you can calculate basically how much of the observation do you think you'll complete.
Okay.
So you can tell, I think we'll complete this observation sort of 80% of the way. And we have a threshold that says 70% is good enough.
And
yeah, so in a way, this is sort of handled from the side of the code that the observatory already has for estimating observing conditions. We're more concerned with what will those conditions be like a few hours or a few weeks from now. But yeah, absolutely, that is potentially a problem, and it's a simplifying assumption that we've made. So yeah.
I think you have to think about in this case, it's almost not taking pictures. Like if you take a picture and somebody walks in front of you, your picture is crude, so you can use it. But since you have the thing observing for an hour, if somebody walks in front of you, you might not even notice it in the whole integral of the picture, right? So because you're integrating all the photons that are coming, then basically you might not even look at that. Or on the other hand, you're observing, weather is getting bad, but you already have, maybe an hour or 20 minutes or 30 minutes of good data in there.
okay.
And that would probably not find the faintest things in that image, but the other things you're gonna see them. So it's a hard thing to say if this is a good or a bad data set.
Okay.
And actually, in some cases, they even find that this is a bad data set after they process it and after they get to the end. So they capture the data, they do the processing to give it to the astronomer. Then some human goes and says, "Oh, this is signal noise. It's really bad. So we cannot give this to the astronomer." And that's by the end of the process.
Okay.
So that's a quality control that's horrible, because it's after you've lost time observing, after you lost time processing, after you lost everything in the middle. Yeah.
And is there a way to learn? So I need at least this amount, and it will improve if I get.
That's what Justin was saying. Like they have this sort of thresholds where, okay, if I have 70% of the time of this scheduling block inside, then it's highly probable that I have everything there. It's the metric of atmosphere stability, whatever that is, right? There's a metric there that we don't know what it is, but they measure this thing called atmospheric stability. If that thing is around this gap, then things should be fine, right?
Yeah.
But everything's sort of, you might think that things are, pure cuts of
Scientific,
right?
Yeah.
But it's sort of
in the ballpark.
Yeah, so there are many such simplifications that we made in consultation with the people at ALMA to make this actually tractable and doable within a reasonable time frame. But I think there's lots of things like that you might pick at to improve. And there are interesting mathematical problems in their own right. So yeah.
The same thing with the configurations, right? You might think that you can do any type of configuration, but since you need to know the inverse of what they're capturing to actually deconvolute the data to get the image, you cannot just put random configurations into the set and try to solve the inverse problem for every single possible combination there. It's impossible. Yeah. I have one question. Can you comment a little bit on, just for people, because in general, when you see these sort of problems, people say, well, machine learning, right? Throw everything to the computer, and try to see if something sticks. Yeah. But we actually tried reinforcement learning for doing sort of thing. If you can give a little bit of a comment on why this doesn't work.
Yeah, well, you yourself were saying this an hour ago. The reason is there's actually a lot of structure. Number one, the state space is absolutely massive. Number two, there's a lot of structure and a lot of intuition that we can take advantage of using a combinatorial optimization approach, right? So if you try to, maybe there's some other way to use reinforcement learning, but if you try to just from scratch learn, here's your 4,000 observations, pick one at every time step, you're throwing away a massive amount of information and exploring an absolutely absurd state space. So I think just kind of naively training a reinforcement learning algorithm, it's just never going to get you far. Yeah,
it was really bad, actually.
Yeah. I am still, I think going forward, I'm interested in like hybrid reinforcement learning optimization approaches, right? So you can use an optimizer to give some structure to a reinforcement learner.
But I think if you use like weather to predict, and you use just the reinforcement learning and that stuff only on weather itself.
The problem is that you wanna try to do the reinforcement learning on the combinations of things. And since you have ALMA, its whole life is 10 cycles, 4,000 projects per cycle, so you have 40,000 data points, and that's basically it. Yeah. Like Didi or Uber, that does that in half a second of users moving around. So sure, they can use reinforcement learning for routing taxi cabs and people because they generate orders of magnitude more data than they have at ALMA to do anything.
But the problem you have here in the schedule is it's actually you don't have a setup time. It's actually your problem here on scheduling is that you're not able to finish the observation. Is you're not looking at sort of the order. If you have the perfect weather, the order would not affect the efficiency of the system. And what you're looking here is sort of to predict the weather, the probability that it's going to go below your threshold. And maybe if you try just to predict weather and use.
Yeah, with Camila, what we thought about this problem was like, think of it as a huge knapsack, but it has pockets in them. And each pocket is a configuration.
Exactly.
You may get some pockets bigger or smaller. That's your sort of wiggle room for doing things, but that's it. You have 365 days a year. Exactly. There's nothing more you can get out of a year, right? And so how do you allocate things into these pockets to ensure that you have the highest, whatever metric you want to grab there? That's also another really interesting talk on, how you come up with an interesting metric to evaluate a schedule. And the first time we talked with them was like, well, we want to maximize Nobel prizes. Sure, I would love that too, right? But that's something you get 10 years down the road, right? So it's not something you can actually use.
Guys, we're just on time and they're going to probably use this room. So thank you very much, Justin.
Thank you.
Por venir y nos vemos en una próxima sesión. Gracias.